Hello, I'm Peyton, and this is Physics 1, Lab 5, and today we are going to be looking at someone dropping a slinky, and we're going to be tracking the motion of it. So, the intro, purpose of this lab is to understand the fundamental physics and motion of dropping a slinky. By tracking the bottom of the slinky, we can look into the different forces interacting on the slinky, and in terms of comparison, we have a tracker video of the slinky, and we took the data out of that, and now we're going to compare it to GlowScript. So real life versus simulated. And here are the fundamental physics involved. First of all, Newton's second law. An object's acceleration depends on the force acting upon an object and the object's mass. Drag, it's pretty much just that air particles will slow things down as they're falling. They just kind of get in the way, so it kind of slows it down. And then gravity. I mean, here at gravity is just, it's the force that the Earth exhibits on the object, so nothing too crazy. And then here the net force is just going to be the change in position or change in time. Vf equals vi plus f net over m delta t, very easy, Newton's second law. Position update, velocity update, and here the force of gravity, which would also be the net force, is, or excuse me, not the net force. Force of gravity would be the only force acting on it right now. It's 0, negative mg0. Besides him holding it up once he releases it, it's just the force of tension and spring and the force of gravity. That's the net force. And here's the video. You'll see it's really short, but the system's the spring, the surroundings Earth. That's it. You dropped it. Let's look at it one more time. Boom. As you can tell, there's only about 15 or 16 frames. Not very many. But yeah. So here is some of the GlowScript code. This is the initialized stuff. So g equals 9.8, t, we're going to start where t equals 0, and change in time, delta t is equal to 0.033, which is how many seconds per frame goes by. And then for the drag, I just kind of messed around until I figured out what I thought was an appropriate drag, which was 0.5. And then while t is less than 0.154, which is where the spring, if you ever drop a spring, you might realize the bottom doesn't move until the top hits the bottom. So 0.154 is where that point happens. So until then, the bottom of the spring stays exactly where it is. And then over here, it's after. That's whenever the position of the spring will start moving too. So over here, bottom, gravity's acting on it technically, but it's not moving anywhere. And then on the right side, gravity's acting on it, and it's moving. So it's literally just difference of, is it, this one, it's kind of floating, and this one is not floating. And then here is the graphs. You can kind of see this one looks like a staircase. That would be because as you saw, the video was so fast that whenever I was actually tracking everything, that it kind of was in choppy segments. So it'd be like it's sitting on the origin, which is where the bottom spring was set, or the origin was set at the bottom of the spring. So sitting on the origin, and then boom, it dropped, and then it's right here underneath the origin, and then dropped, and it hit the ground, and yeah. Which that's not what happens when you drop a spring. This is what happens when you drop a spring. So it'll be sitting at the origin, and then gravity, which is a constant force, will act on it, and it will drop until it hits the ground. So this is much more accurate, but this was the video. And then possible source of error, literally what I just talked about, it was that the video was just so fast. I mean, it was like, what, a second, not even, that only a few frames were actually accounted for. But I think the GlowScript graph is an accurate representation of what happened in real life. But anyway, last lab's over. It's been fun.